All right, Class 5 Worksheet, Chapters 8 and 9. All right, so a hypothesis test is a statistical method that uses sample data to evaluate a hypothesis about a population. Okay, so that's the main thing that we'll be doing the rest of the semester is taking sample data and comparing it to a population or comparing it to an estimate about a population. All right, so the null hypothesis states that in the general population, there is no change, no difference, or no relationship. In the context of an experiment, HO, that's what it's labeled as, predicts that the independent variable, which is the treatment, or the manipulated variable, has no effect on a dependent variable, the scores, or whatever we're measuring for the population. Okay, so the null hypothesis in a research study is what we write when we say that we're not going to find any significant result between whatever we're measuring. The alternative to that, which is the alternative hypothesis, labeled as H1, which is also known as a research hypothesis, states there is a change, a difference, or a relationship for the general population. In the context of an experiment, H1 predicts the independent variable, the treatment, or the manipulation does have an effect on the dependent variable, and it does not only have an effect on the dependent variable, it has a significant effect on a dependent variable. All right, that's why we test, for example, our T obtained scores against the T critical values, and that's how we know if we reject the null hypothesis, which means that there is significance, or we fail to reject the null hypothesis, which means there's no significance. So the alpha level or level of significance is a probability value that is used to define the concept of very unlikely in a hypothesis test. So the alpha level corresponds with the critical value that we're comparing our obtained score to. And if we're able to meet that or beat it, we could state that it's very unlikely this happened by chance, and the result that we're showing is a good, valuable, true result, and we're showing an effect based on the manipulation that we did in the experiment. The critical region is composed of extreme sample values that are very unlikely, as defined by the alpha level, to be obtained if the null hypothesis is true. So if there's no effect of the manipulation, then the null hypothesis will be true. But if the treatment effect or the manipulation to whatever we're studying or researching on has an effect, then if our value comes to be at that critical region or above it, then we know that we have a good result, and we could state with confidence, we can never say 100%, but we could state with 95% confidence to 99% confidence, right? Based on a 0.05, we could say 95%. 0.01, we could say 99%, that we got these results and it wasn't by chance. All right, a type 1 error. All right, a type 1 error is when we say there's a significant result and there's really not. Or we reject the null hypothesis when we should fail to reject the null hypothesis. All right, the alpha level is also the probability of getting a type 1 error, right? So if we're significant at the 0.05 level, then there's just a 5% chance that we're making a type 1 error, a 5% chance that we got these results by chance. If the alpha level is 0.01, then the probability of making a type 1 error is 1%, and that means that we could be 99% confident that we did not get this result by chance, or there's a 1% chance that we got these results by chance. A type 2 error occurs when a researcher fails to reject a null hypothesis that is really false. So a type 2 error is like a miss. Think about a smoke alarm not going off, right? There's actually a fire, but the smoke alarm is not measuring that there is a fire. So the same thing can go for research. It's when there is a significant result in our study, however, we're not finding it, we're not measuring it. And usually that's because we're setting our alpha level too stringent. So an example, let's say we set our alpha level at 0.01 and we find out that the result is not significant, but at 0.05 it is significant. But we tested it at 0.01, so it wasn't significant, but at 0.05 it is. We missed it, right? We missed that there was an effect going on. All right, so a type 2 error is a miss. All right, this chart just explains that, everything I just said. I went over that in class. And right, this is just an example of the critical values from a two-tailed test for a z-table. So this is for z-scores, and it just shows alpha level plus or minus 1.96 at 0.05, plus or minus 2.58 at 0.01, and plus or minus 3.30 at 0.001. All right, so we have to hit these values or be beyond them to say that we got a significant result, right? And it's the same concept for the t-tests. Right, a result is said to be significant or statistically significant if it is very unlikely to occur when a null hypothesis is true. That is, the result is sufficient to reject the null hypothesis. Thus, the treatment has a significant effect if the decision from the hypothesis test is to reject the null. In a directional hypothesis or a one-tailed test, the statistical hypothesis specify either an increase or a decrease in the population mean. That is, they make a statement about the direction of the effect, right? So, right, we know we did that in class 2, right? This is a two-tailed test, so a one-tailed test, as we know from studying the t-tables, the values change on a two-tailed or one-tailed test, right? And when we go to power, we'll see that, right, it's easier to get a significant result on a one-tailed test than on a two-tailed test because the alpha level, well, the critical value will be lower, so you have a better chance of getting a significant result. All right, and a directional hypothesis test is just usually, we're looking for more or less, greater or less than. You'll see a direction in the question. And a measure of effect size is intended to provide a measurement of the absolute magnitude of a treatment effect, independent of the size of the samples being used. So one of the ones that are commonly used is Cohen's d, where you take the mean difference divided by the standard deviation. And Cohen's d actually refers to whatever the Cohen's d value is, what is the standard deviation difference between the sample mean and the population mean. Okay, so Cohen's d is actually a measurement of standard deviation. So power of a statistical test is the probability that the test will correctly reject a false null hypothesis. That is, power is the probability that the test will identify a treatment effect if one really exists. So a good way for that to be done is you want to have a large sample size, right, a larger n. You want to be comparing it to a smaller variance, right? So you want to have a smaller variance that you're comparing it to, because then if you show that you are further away from what most of the population does, with whatever treatment or intervention or manipulation that you're using, then that gives a lot of power. So you want to compare it to a population that has a known smaller standard deviation or a smaller estimated standard deviation, as we do in t-tests, because it holds more weight. It gives us a better result and a better chance of getting a significant result. And again, a one-tailed test, as I just explained before, that gives more power because it is easier to reject the null hypothesis using a one-tailed test because the critical values that come along with a one-tailed test are smaller than the critical values with a two-tailed test. And a higher alpha level, of course, because the higher you set your alpha level to, the lower the critical value will be. So it will be easier to say you have a significant result, but there also becomes a problem with that because the higher you set your alpha level to, you raise your chance of getting a type 1 error more. And when we do that, we could be saying that we're finding a significant result when we're really not. All right. In an experiment, people are told to solve a problem by focusing on the details. Is the speed of solving a problem different, keyword different, for people who get such instructions compared to the speed for people who are given no special instructions. So I'm asking you to give the two populations that are compared. So people who get special instructions and people who are not given special instructions, right? The general population of problem solvers. So the null hypothesis, which stating there will be no effect, would be the speed of solving a problem for people who receive special instructions is not different compared to the speed for people who are given no special instructions. And the alternative or research hypothesis is just the opposite on a two-tailed test, right? And we know it's two-tailed because what do we hear? We hear difference. So if you're hearing it, is there a difference? We're not looking at a direction, so we must use a two-tailed test and test both sides of the distribution. The speed of solving a problem for people who receive special instructions is different compared to the speed for people who are given no special instructions. Is it a one-tailed test or a two-tailed test? Well, it's a two-tailed test because we do not predict a direction of the effect. Based on anthropological reports in which the status of women is scored on a 10-point scale, the mean and standard deviation across many cultures are known. A new culture is found in which there are unusual family arrangements. The status of women is also rated in this culture. Do cultures with the unusual family arrangements provide higher status to women than cultures in general? So higher status, right? It's signifying a direction, so we know it's a directional hypothesis on the positive side. Give the two populations, cultures with the unusual family arrangements and cultures in general. State the null hypothesis. Cultures with unusual family arrangements provide lower, not higher, or the same status to women than cultures in general. So when you're stating the null on a directional hypothesis, you want to give the opposite of what the research is looking for or the same. So we're looking for higher status, so we want to mention arrangement will provide lower, not higher, or the same. And then the research, cultures with unusual family arrangements provide higher status to women than cultures in general. And this is a one-tailed test, and we know why, because of this word higher status that we're looking for. Do people who live in big cities develop more stress-related conditions than people in general? So when you're reading questions, you see more, you already know, okay, it's going to be a one-tailed test in a positive direction. Give the two populations that are compared, people who live in big cities, people in general. And null hypothesis, people who live in big cities develop less stress-related conditions or the same than people in general. Again, we're looking for more stress-related conditions, so the null will be less stress-related conditions or the same. State the research alternative hypothesis. People who live in big cities develop more stress-related conditions than people in general. And it's a one-tailed test, right, because we're looking for a direction. All right, on to chapter 9. Know all those. So basically what I just went over will be, the bulk of your multiple choice questions on your second exam. All right, and then the rest will be computations from chapter 9, 10, 11, and 12. So the T statistic is used to hypothesize about an unknown population mean U when the value of the standard deviation is unknown. All right, so we know we're given, when we're doing a single sample t-test in chapter 9, we're always going to be given mu, but we're not going to be given a standard deviation. So we'll be estimating the standard deviation of the population. All right. So evolutionary theories often emphasize that humans have adapted to their physical environment. One such theory hypothesizes that people should spontaneously follow a 24-hour cycle of sleeping and waking, even if they are not exposed to the usual pattern of sunlight. To test this notion, 8 paid volunteers were placed individually in a room in which there was no light from the outside and no clocks or other indications of time. They could turn the lights on and off as they wished. After a month in a room, each individual tended to develop a steady cycle. Their cycles at the end of the day were as follows, and they give the data: 25, 27, 25, 23, 24, 26, 25. Use the 0.05 level of significance. Using the 0.05 level of significance, what should we conclude about the theory that 24 hours is a natural cycle? So the null here would be the average cycle length under these conditions does not differ significantly from 24 hours, all right? Because the null is always going to state that there's no difference between what you're comparing. And the research will say that there is a difference, whether it's directional or not. And here they don't indicate a direction. They just want to know if this hypothesis holds weight, as a student said. So The average length under these conditions differs significantly from 24 hours. One-tail test or two-tail test. So it's a two-tail test in this case because no direction implied in research question. Independent variable, there's two levels here, right? There's the group that's not exposed to usual pattern of sunlight or time, right? And that was the sample, right? Because they were not exposed to any sort of time as well, right? The clocks were taken away. They couldn't look at any sort of time like that. And there were no windows, so they couldn't see any sunlight. And the population is everybody else in the world exposed to usual patterns of sunlight and time. The dependent variable is time cycle in hours, right? The dependent is always what's being measured, and what was being measured was the cycles of the participants. So the critical t-values, right? Well, they said it's the alpha level is 0.05. We know it's two-tailed because no direction was given. Degrees of freedom is 6 because n equals 7, so df equals n minus 1, so 7 minus 1 is 6. You go to the chart, you go to df of 6, you go up, you look for 0.05 two-tailed, and you go down, and you'll see that it's plus minus 2.447. So we have to be at that point or greater than it on either side of the distribution to say that we have a significant result. The population mean is 24, right? We all know 24 hours is the known cycle, right? That's a population mean that we all know. Sample mean, right? You just add up all the sample values, divide by n, and you'll get 25. Sum of squares, we did this before. You could do it one of two ways. I showed you guys in class that the definitional formula works well here, but you can also, always use the computational formula. You just get the sum of x squared and the sum of x, and, we did that. If you still have trouble with that, then go back to the video on chapters 2 to 4. All right, sample variance is SS over DF. Or SS over n minus 1. They mean the same thing. So you just plug in the SS value over n minus 1, you'll get 1.67. Sample standard deviation, which we're using for Cohen's d, is the square root of s squared, right? So SS over DF equals s squared, which is also the sample variance. So the square root of that is 1.29. All right, remember, variance and standard deviation, they go hand in hand, right? Standard deviation squared is the variance. The square root of the variance is the standard deviation. All right, now we're going to estimate the standard error. Remember with z-scores, we had the standard error because we had actual population mean and a population standard deviation. But here we are estimating the standard error. So estimated standard error of the mean, estimated population standard error. All of them do work, so we'll just say standard error of the mean. They all mean the same thing, right? So the square root of the variance, s squared, which is the variance of the sample, which is also known as the estimated variance of the population, divided by n, plug it into the formula, you get 0.49. And then for the t-test, it's just m minus mu over sm, which we just computed, right? The mean of the sample is 25. The mean of the population is 24. Divide by 0.49. It's 2.041. And right away, we could just go look. What was the critical value? The critical value was 2.447. So is it significant? No. There was some effect, and we'll check that right now. So even if something isn't statistically significant, there could still be an effect size. So if you do the Cohen's d effect size, you do m minus mu over s, right? And s is this value up here. S is the sample standard deviation, 1.29. So you just take the deviations from the mean, which is 25 minus 24 divided by 1.29, and you get a 0.78, right? A 0.8 is a large effect. So it's almost a large effect. So you would say medium to large effect here, but it is almost a large effect size. So there was an effect in this study. However, it wasn't statistically significant, and most likely it wasn't statistically significant because there wasn't enough participants. If there were more participants in this study, it might be statistically significant. So if we see an effect size like that, And, we were not too far off from the critical value. You might want to do this study again with more participants, but then again, a study like that where, you're locking someone in a room for 30 days, I'm sure they get paid very well to do that. And money is always an issue. So it's probably hard to get a large amount of people to do that study. Right? But we can assume, possibly, we should never assume, but I would say it's very possible if we double the sample size, we might find a significant result. And I'm going based off the Cohen's d effect size. All right, and then R squared. So that's the percentage of variance explained by the manipulation of the independent variable. All right, so 41% is explained here by the independent variable. All right. Obviously, the higher you get to 100, the better the effect. But a 0.41 is still a good amount, saying 41% can be explained by the independent variable. And to get R squared, you just take T squared divided by T squared plus DF. And remember that T squared is your obtained T value. It is not the critical T value. All right, and remember, T values are always rounded to the third decimal point, because if you look at the T table, they're all to 3 decimal points. You plug it in, and that's how you get it. Now, what are we going to do? Reject or fail to reject, and we are going to fail to reject the null hypothesis because the obtained value is less than the critical value. All right. It is known that the average times a romantic couple breaks up before getting married is 2.5 times. That it is known. That's the population mean, right? That's one way that they'll say it's population mean. It might not always say mu equals 2.5. You might just say if it is known, the average. If it's a known average, that means it's a known population mean. A researcher wants to know if married couples from New York City broke up more before they were married than couples in general. A sample of 7 married couples from NYC breakup amounts before marriage are as follows: 5, 1, 2, 3, 4, 4, 3. Using the 0.05 significance level of using the 0.05 level of significance, same thing. Find out if NYC couples break up more before marriage than couples in general. So more, you see that more, it's going to be a directional hypothesis. So the null hypothesis has to state the opposite or the same. So couples in New York City break up less or break up the same before marriage as couples in general. And couples in New York City break up more before marriage than couples in general. What type of test? One-tailed test. What gives it away more? Independent variable are people who live in the 2 levels of them are people who live in big cities and people in general. That is what's being manipulated. People live in big cities and people in general. And what are we measuring them on? We're measuring them on breakup amounts before marriage. All right, so people live in big cities. You could also say couples who live in big cities. All right, either one would work here. Couples might be a better way to put it. However, if you put people on this question on a test, I would still give you full credit for it. Dependent variable, breakup amounts before marriage. So the critical T value, right? We know the degrees of freedom is 6 because 7 minus 1 is 6. It's one-tailed. On the positive side with the alpha level of 0.05. So you go to 0.05, one-tailed, degrees of freedom of 6 on the T chart, and you will get a 1.943. And since we're looking for more, it'd be a positive 1.943. Population mean given 2.5. Sample mean, addable to scores, divide by n, 3.14. Sum of squares, again, you could do it multiple different ways. Right here, I'm showing you the computational way. Again, I'm not going to go too much over this. Again, refer to the video on chapters 2 to 4 if you need help with sum of squares. Sample variance, SS divided by n minus 1, or SS divided by DF. Either one means the same thing. Just plug it in. S squared is 1.81, which is the sample variance or estimated variance of the population. Sample standard deviation, again, we use it for Cohen's d. I put that there not to confuse you, just so you know when you're going to use it. Is just the square root of the sample variance, which is 1.35. Now, the estimated standard error, which is the denominator of the t-test, is the the square root of s squared divided by n. And if you plug that in, you will get 0.51. And the obtained t-value is m minus mu over sm. So and the mean is 3.14. The mean of the sample, that is 3.14. The mean of the population is 2.15. And the standard error, or the estimated standard error of the population is, or the sample standard error is 0.51 equals 1.255. Estimated Cohen's d effect size. That's when we're going to use S. So 3.14 minus 2.5 divided by 1.35 equals 0.47. All right, so if you look at the Cohen's d chart, 0.47 is a small to medium effect size. So if I asked you to report it, it would be a small to medium effect size. A percentage of variance explained. Again, and those kind of questions will be more on your multiple choice than the actual computations. Percentage of variance explained, r squared. Again, take t squared over t squared plus df. Just plug the values in, you get 0.21, so you can say 21% of the variance is explained by the independent variable, or by the treatment effect, or by the manipulation of the independent variable. And fail to reject or reject, we're failing to reject because the t obtained is smaller than the t critical. Last question for this video. In a particular country, it is known, again, population mean, that college seniors report falling in love an average of 2.20 times during their college years. A sample of 5 seniors originally from that country would have spent their entire college career in the United States were asked how many times they had fallen in love during their college years. The mean for this sample was 3.4, and the sample variance is 2.3. So we're given more information than we were in the previous questions. Using the 0.05 significance level, do students like these who go to college in the United States fall in love more often than those from their country who go to college in their own country? So the null hypothesis, so we have to look more often, right? So more often, what does that give away? One-tailed test, so we have to write the null hypothesis as such. Students who go to college in the United States from the particular country fall in love less often or the same than students who go to college in that particular country. And the research, students who go to a college in the United States from a particular country fall in love more, because that's what we're looking for. Fall in love more often or the same as students who go to college in a particular country. All right, that is an error. More often or the same. It should not say or the same, okay? Typo, my apologies. It should just say fall in love more often. So it should read, students who go to college in the United States from a particular country fall in love more often than students who go to college in that particular country. I will change that on the answer key as soon as this is over. One-tail, two-tail test. One-tail, positive, keyword, more often. Independent variable. Students who go to college in the United States from a particular country, right? That's the sample. And students who go to college in that particular country, the population of that country of students who go to college there, right? Those are the two populations that are being measured. And what are we measuring? We're measuring the amount of times fallen in love. And we're looking to see if there's a difference, that if they come to the United States from that country, do they fall in love than the students from the country that don't come to the United States. T-values, so we know n equals 5, so df must equal 4. The alpha is 0.05. So you just use those 3 values, you go to the T chart, and you'll get a T critical of 2.132. If it's a positive, you don't have to put the positive sign in front of it. But if it's a negative, you must, or you'll lose points. Population mean, given 2.20. Sample mean, in this case, it was given 3.4, right? So we just didn't have to solve for that. And sum of squares is not needed with the information given, right? We compute the sum of squares for what, right? We do it to get the variance and standard deviation. So if we're given the sample variance, which you can see in H, it was given, then we don't need to compute it. So S squared was given, which is 2.30. So the sample standard deviation, again, used for Cohen's d, is just the square root of question H, right? It's the square root of the sample variance, which is 1.52. The estimated standard error is the square root of the variance that was given over n, and plug those in, you'll get 0.68. Obtained t-value is just m which is the sample mean, minus mu, population mean, over SM, which is the estimated standard error, or the standard error of the mean, or the estimated standard error of the mean. And that's 3.4 minus 2.2 divided by 0.68, which equals 1.765. Estimated Cohen-D's effect size. So you just take the mean difference, divide by S, and it gives you 0.79, right? There is a large effect there, right? Almost, right? If it was 0.8, it'd be large. So it's medium to large, but it's just missing a large. And percentage of area explained, R squared, is 0.44. You just put in the t values. T squared, your t obtained squared over t obtained squared plus the degrees of freedom. You get 0.44. We fail to reject the null. T obtained is smaller than t critical. Again, I want you all to start understanding what was the n here, right? N was 5, right? It's a small sample size. So we're seeing a large effect, but because of that small n, you got to get an even bigger t obtained to say that it's statistically significant. However, you can see that there's an effect size. So a lot of researchers will go and look for effect sizes on non-significant results and figure out why there was an effect, but it wasn't significant. And most of the time it's because the sample size was too small. And then they'll go run it again with a larger population, even though you'll have, a larger sample size, because they might think that it's financially worth it to invest into more participants because they will get the result that they're looking for. And again, R squared, percentage of variance explained, 0.44, and fail to reject the null, T obtained is smaller than T critical. And this question, do on your own, and we can go over that during the review. We'll also be going over a whole review sheet, and see you guys in class. Good luck studying.